There is a place in our solar system where the ground moves, not from earthquakes, not from tectonic drift, but because something out there is squeezing it rhythmically, relentlessly like a hand clenching and releasing a ball of clay, and what comes out from the pressure isn't water or gas or anything we'd associate with a world orbiting 400 million miles from the sun. What comes out is fire. That sentence should bother you. Fire doesn't belong out there. Nothing warm belongs out there. The sun is so distant from Jupiter's orbit that it delivers roughly 4% of the energy it gives Earth. 4%! At that distance, water doesn't just freeze, it becomes structural. It forms the bones and bodies of moons. Ice is what the outer solar system is built from. And yet here, on a rocky, metal-dense moon called Io, you have active volcanoes. Hundreds of them, more than on any other body we've ever found. And that's not the disturbing part. The disturbing part is that this moon should not be volcanically active at all. There's no internal radioactive decay powerful enough to explain it. There's no residual heat from formation that could still be running after 4.5 billion years. By any standard model of planetary science, Io should be cold and dead and quietly frozen, and instead it is, by every metric we can measure, the most volcanically violent place in the entire solar system. And we've only recently started to understand why. Hold on to that question, why? Because the answer is going to open several others that no one has cleanly resolved. Jupiter is not a planet that makes sense at human scale. It is 11 times wider than Earth. More than 1,300 Earths could fit inside it. It contains more mass than every other planet in the solar system combined, with enough left over to nearly build a second one. Orbiting this object are nearly 100 recognized moons, ranging from captured asteroids barely a kilometer across to worlds larger than the planet Mercury. But 4 of those moons are exceptional. They are large enough and bright enough that a man in the 17th century, using a crude handmade telescope that you could find in a toy store today, was able to spot all 4 in a single night. His name was Galileo Galilei, and what he saw became the first direct evidence in history that not everything in the cosmos orbited the Earth. These 4 bodies, Ganymede, Callisto, Europa and Io, are now called the Galilean moons. 3 of them behave the way you'd expect moons at Jupiter's distance to behave. Ganymede and Callisto are frozen worlds, heavily cratered, geologically inert. They have been sitting in the same approximate state for billions of years, slowly accumulating craters from asteroid and comet impacts, going nowhere fast. Europa is more interesting. Its smooth, icy surface hides a liquid water ocean that may be the most promising place in the solar system to search for microbial life. But even Europa is covered in ice. Cold is the theme out here. Cold is what the physics predicts. And then there's Io. Io is the innermost of the 4, orbiting at roughly 350,000 kilometers above Jupiter's cloud tops, about the same distance as our moon is from us, and it looks at first glance like it simply does not belong to the same system. Where the others are grey and white, Io is yellow and red and black. Where the others have craters, Io has almost none. That absence of craters, which took scientists a moment to fully appreciate, tells you something profound. The surface of Io is being replaced faster than impacts can scar it, constantly, continuously. The ground you see today was not the ground that existed 10,000 years ago. In geological terms, that is an eye blink. In human terms, it is incomprehensible. This matters later. Remember the absence of craters. The first close images of Io came in 1979 when the Voyager 1 spacecraft swung past Jupiter on its way out of the solar system. Even at a distance of 20,000 kilometers, with cameras that were primitive by any modern standard, Voyager captured something that stopped scientists cold. 9 active volcanic eruptions happening simultaneously, visible from space. Plumes of sulfur gas rising hundreds of kilometers into the vacuum. Lava flows spreading across the surface in real time. No one had expected this. The models didn't predict it. And in the years immediately after Voyager, the question that dominated Io research wasn't what was erupting, it was where the energy was coming from. To understand the answer, you need to understand something about gravity, not the familiar concept of things falling down, but gravity as a shaping force. A force that reaches through space, grabs a world and physically deforms it. Jupiter's gravitational field is immense, and because Io orbits so close to the planet, that field is not uniform across Io's body. The side of Io closest to Jupiter is pulled significantly harder than the side facing away. This differential, this gradient, creates what's called a tidal force, and tidal forces don't just pull, they stretch. They distort. On Earth, our Moon's tidal force is strong enough to lift the ocean by half a meter on average. Half a meter of water, continent scale, raised and lowered twice a day by the Moon's gravity. That seems dramatic until you appreciate what Jupiter does to Io. On Io, Jupiter's tidal force lifts the solid rock surface, by up to 100 meters. When Io is at its closest point to Jupiter, the ground itself deforms upward by 100 meters and then slowly relaxes as the Moon moves away. Not water, not loose sediment, solid, rock, moving. This is a kind of violence that the phrase tidal force does not adequately convey. But why does Io's orbit bring it that close repeatedly? Why isn't it just circular at a fixed, safe distance? This is where the other moons become important. Io does not orbit Jupiter alone. Europa, Ganymede, and Callisto are also there, and their gravity tugs on Io not powerfully, not compared to Jupiter, but persistently. That persistent tugging, applied over billions of orbits, has locked Io, Europa, and Ganymede into a gravitational pattern called an orbital resonance. For every 4 times Io orbits Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. These are not approximations. They are exact, self-reinforcing ratios, and the gravitational interactions that maintain them are what prevent Io from settling into a circular orbit. Every time Io approaches certain points in its path, it receives a rhythmic gravitational nudge from Europa. That nudge keeps the orbit slightly elongated elliptical so that Io's distance from Jupiter cycles constantly. Near, then far, near, then far, once every 42 hours. This seems like an orbital mechanics technicality. It is also the reason Io is alive. Every time Io swings close to Jupiter, the tidal force ramps up. The rock stretches. Every time Io pulls away, the force relaxes. The rock releases. This happens constantly, rhythmically, hundreds of millions of times over the age of the solar system. All of that repeated deformation generates heat the same way a metal paperclip gets warm if you bend it back and forth quickly. On the scale of an entire moon, bent by Jupiter's gravity, that heat accumulates to a degree that overpowers everything else. It melts rock. It drives convection. It powers 400 volcanoes simultaneously. This process is called tidal heating, and Io is its most extreme known example. Now here is where the first model breaks down. The natural assumption, and scientists held it for years, was that Io must have a global magma ocean beneath its surface. If tidal heating is generating that much energy uniformly across the whole moon, then the interior should be a continuous molten layer, like a planet-scale lava lamp, with a solid crust floating on top. Clean, simple, satisfying. It's also wrong. When spacecraft were able to map Io's gravitational field in detail, they found something inconsistent with a global magma ocean. The gravitational pull around Io isn't uniform. It varies in ways that suggest the molten material inside is not evenly distributed. Instead, the current best model is that the heat concentrates in localized regions, pockets of molten rock, positioned in the parts of the moon that experience the most intense tidal flexing, not a single ocean. Hundreds of separate isolated reservoirs, each one feeding a distinct volcanic system, each one behaving somewhat differently from the others. This means every volcano on Io has its own internal plumbing, its own timescale of activity, its own behavior. That explains the 400 volcanoes. It does not explain the mountains. And this is where things stop making sense in a different direction. Io has no plate tectonics. The mechanism that builds mountains on Earth, the collision of crustal plates forcing rock upward, simply doesn't operate on Io. There are no plates to collide. The crust is a single continuous shell, constantly being resurfaced from below by volcanic activity. So, when early images showed volcanic calderas and lava fields across Io's surface, that matched what the models predicted, but the mountains didn't. There are mountains on Io that rise 18 kilometers from the surface. For reference, Mount Everest is roughly 9 kilometers high. The tallest structures on Io are twice the height of the tallest mountain on Earth. And unlike Everest, which sits within the Himalayas, part of a vast elevated range formed by the collision of two tectonic plates, Io's mountains are isolated. They appear alone, without context, without ranges. A spike stabbing straight up from an otherwise flat volcanic plain with nothing of comparable height for thousands of kilometers in any direction. This is not how mountains form on Earth or Mars or anywhere else we've studied. The morphology is alien in the most literal sense. The current leading explanation is, once you understand the volcanic dynamics of Io, almost grimly logical. Io's surface is being continuously buried by volcanic material. Lava flows and sulfur deposits accumulate over time, pressing down on the existing crust with tremendous weight. That downward pressure has to go somewhere. It can't compress the rock indefinitely. So in localized areas where the accumulated pressure exceeds the strength of the surrounding material, the crust fails not downward but upward. It erupts in a different way, not as a volcano, but as a mountain. A sudden compression-driven uplift that pushes a block of crust skyward faster than anything on Earth would recognize as a geological process. There is a mountain on Io named Steeple Mountain. In silhouette, it resembles the spire of a cathedral, narrow, pointed, improbably tall for its base. It stands somewhere between 5 and 7 kilometers high, and its shape is unlike any structure formed by the known mountain-building processes on any rocky world. It is not alone. Juno's close flybys in late 2023 and early 2024 revealed that Io is dotted with similar structures. Lone spires, abrupt and isolated, scattered without pattern across the volcanic surface. Each one a product of this compression mechanism, each one representing a moment of geological rupture that happened fast. Fast in geological terms still means thousands of years to human experience, but on a moon like Io, thousands of years is long enough to be buried again. The mountains that exist now are in a constant race, rising from compressional uplift on one timescale, being buried by volcanic resurfacing on another. The ones we can see today won temporarily. Now set aside the mountains for a moment and think about the surface itself, what it looks like, and what that appearance is actually telling you. Because the colors of Io are not incidental. They are a direct readout of the chemistry, the temperature, and the recent history of volcanic activity across the entire moon. The dominant element coloring Io's surface is sulfur. Sulfur is abundant in volcanic systems throughout the solar system on Earth. The round holes in lava rock are the remnants of sulfur gas bubbles trapped and released during cooling. On Io, where volcanic activity operates at a scale hundreds of times beyond anything on Earth, sulfur is everywhere. But sulfur is a chemically versatile element. Under different temperatures and pressures, it takes on dramatically different forms, and each of those forms reflects a different color. The yellow regions on Io's surface are sulfur that has been frozen by the extreme ambient temperatures, crystallized solid, essentially sulfur snow. The white and pale blue patches are frozen sulfur dioxide, the coldest material on the surface, found in areas that never receive direct sunlight. The green is sulfur monoxide, produced in the upper atmosphere by Jupiter's powerful radiation belts interacting with the volcanic gas. And the red and black regions are the fresh ones, areas where the sulfur is still hot, still active, still being processed by ongoing eruptions. You are, in effect, looking at a temperature map of a world's volcanic history, written in color. Yellow is cold history, red is recent fire, and somewhere on the boundary between them, new eruptions are already beginning. There is also something strange about the atmosphere. Io has one, which is already unusual for a moon its size at this distance from the Sun. It's primarily sulfur dioxide, thin and variable, and it shouldn't be stable. The atmospheric pressure on Io shifts dramatically depending on where you are and what time of day it is. The sunlit hemisphere has a slightly denser atmosphere than the night side, because sulfur dioxide freezes out of the air when temperatures drop far enough. Every dawn on Io is, in a sense, a new atmospheric event gas sublimating off the surface as sunlight hits, building the thin layer back up from frozen deposits. Every sunset, is the reverse. The atmosphere partially collapses and refreezes. On Earth, this kind of atmospheric behavior would be catastrophic. On Io, it is simply Tuesday. And then consider the radiation. Jupiter possesses the most powerful magnetic field of any planet in the solar system, and that field traps high-energy charged particles in radiation belts that orbit the planet. Io sits squarely inside the most intense zone of those belts. The radiation environment around Io is severe enough to damage spacecraft electronics over extended exposure. It's part of why missions to the Jupiter system plan their trajectories carefully to minimize time near Io. For anything on the surface, the radiation dose would be lethal by any biological standard within minutes. Whatever chemistry is occurring on Io's surface is happening under constant particle bombardment, which means the molecular environment there is actively reactive in ways that are difficult to model from Earth. This is worth pausing on. We spend enormous resources searching for life elsewhere in the solar system, and the primary criteria are liquid water, a stable environment, and protection from radiation. Io fails all three categories simultaneously and by enormous margins. It has essentially no water. It is believed to be the driest known body in the solar system, drier than Mercury, the planet that orbits closest to the Sun and is constantly baked by solar radiation. It has one of the least stable surface environments in the solar system, and it receives radiation that would sterilize biological material nearly instantaneously. Io is not a candidate for life, but here is the question worth sitting with. It once might have been a candidate for something we haven't thought to look for yet. The chemistry happening on Io's surface sulfur compounds in multiple oxidation states. Interacting with radiation and heat and volcanic outgassing is not chemistry that planetary scientists have studied in the context of prebiotic chemistry or early planet chemistry. It's too strange, too far outside the water-based frameworks that dominate the search for life. But chemistry that's too strange to fit our existing frameworks is, historically, exactly where the surprises come from. Hold that thought. It becomes relevant at the end. The lava lakes on Io deserve their own treatment because they are among the most extraordinary landforms we've documented in the solar system. On Earth, there are a few persistent lava lakes' active craters where molten rock remains at or near the surface for extended periods. They are rare, geologically unstable, and typically small. The largest active lava lake on Earth is a few kilometers across. On Io, the largest lava lake is named Loki Patera, and it is 200 kilometers in diameter. To put that in geographic terms, Loki Patera is roughly the size of the island of Iceland. In the center of Loki Patera sits a large island of solidified rock surrounded by a churning lake of active molten material. The lake itself isn't still, it appears to overturn on a roughly 540-day cycle as denser cooled crust sinks and hotter material rises from below. This overturning wave propagates around the lake at a speed of roughly 1 to 2 kilometers per day, clockwise. Scientists watching Loki Patera from Earth can track this wave, predict when the next overturning event will peak, and use those predictions to test models of volcanic fluid dynamics. Io's surface is so actively volcanic that it functions, in a sense, as a laboratory. A laboratory where the experiment has been running for 4.5 billion years. Understanding the interior of Io matters beyond the moon itself. The tidal heating mechanism operating on Io is a template, a worked example for understanding volcanic activity throughout the solar system and on exoplanets. There are planets orbiting other stars in tight resonant configurations with other planets. The moons of those planets, if they exist, may experience tidal heating similar to or more extreme than what Io experiences. We've already identified a handful of exoplanet systems where the geometry suggests this kind of heating should be occurring. What we found on Io tells us that such worlds should be volcanic, possibly intensely so, and that volcanism of this magnitude profoundly shapes the chemistry of an atmosphere. If we're going to correctly interpret the spectra of exoplanet atmospheres as we search for signs of life or habitability, something multiple future space missions are designed to do, we need to know what the signature of intense tidal volcanism looks like. Io is our reference specimen. Most of what we know in detail about Io came from 2 spacecraft. The Galileo probe, which operated at Jupiter from 1995 to 2003, made numerous close flybys of Io and produced the first truly detailed mapping of the surface. And then, more recently, the Juno spacecraft, which arrived at Jupiter in 2016, primarily to study the planet's atmosphere, was repurposed after completing that mission to conduct close approaches of the Galilean moons. In December 2023 and February 2024, Juno passed within 1,500 kilometers of Io's surface, closer than any probe had come since Galileo. The images and data returned from those flybys are the clearest pictures we've ever had of this world, and they are what revealed the full strangeness of the mountain distribution, the texture of the volcanic plains, and the sheer variety of eruptive structures across the surface. This is likely to remain our best view of Io for a long time. Juno is running out of fuel, and its eventual fate is a planned deorbit into Jupiter's atmosphere, a deliberate end designed to prevent the spacecraft from accidentally contaminating the moons with Earth microbes after control is lost. The two upcoming missions to the Jupiter system, the European Space Agency's JUICE probe, launched in 2023 and arriving at Jupiter in 2031, and NASA's Europa Clipper, launched in 2024 and arriving in 2030, are directed specifically at the icy moons, particularly Europa. Neither has an Io flyby as a primary objective. There are no approved missions heading directly to Io in any near-term planning cycle. That's not a scientific judgment on Io's importance, it's a resource allocation decision made at a time when Io was less understood than it is now. The revelations from Juno's flybys arrived recently enough that they haven't yet worked their way into formal mission planning cycles, which operate on timescales of a decade or more. The science community has been building the case for an Io-focused mission. Proposals have circulated for orbiting observatories that could maintain continuous monitoring of the volcanic activity, but nothing has been selected. For now, whatever Io is doing, it is doing it without an audience. That absence of observation matters in a specific way. Io's volcanic system is dynamic on short timescales. Individual eruptions begin and end over days to weeks. Large regional lava flows emerge, spread, and cool over months. The overturning cycle at Loki Patera completes in less than 2 years. All of this activity is happening continuously, and we are currently watching it, at best, from Earth-based telescopes and the occasional distant observation from Juno during its final orbits. There are things happening on Io right now that we will never have the data to fully reconstruct. That's a specific, definable scientific loss, and it accumulates with every year. A dedicated mission doesn't exist. There's a broader question hiding inside all of this. Io represents a mode of planetary heating tidal, driven by gravitational interaction rather than internal radioactivity or solar input that may be far more common in the universe than we've historically assumed. For most of the history of planetary science, the discussion of what makes a planet geologically active centered on two things: primordial heat from formation and radiogenic heat from the decay of uranium, thorium, and potassium in the interior. These were the mechanisms for Earth's volcanism, Mars's ancient volcanism, Venus's current resurfacing. Tidal heating was understood in principle, but treated as an exotic edge case. Io changes that accounting. It demonstrates that tidal heating alone can sustain volcanic activity at an extraordinary rate, indefinitely, as long as the orbital resonance is maintained. And orbital resonances, once established, tend to be stable over very long timescales. This means that any rocky moon in a tight resonant orbit around a large planet could, in principle, be tidally heated to a degree that produces active volcanism regardless of how far the system is from its star, regardless of what stage the host planet is in its evolution. The outer solar system, which we had largely written off as frozen and inert, may contain far more geologically active bodies than we've looked for. We've looked at Saturn's moon Enceladus, which erupts geysers of water, ice, and organic compounds from cracks at its south pole, driven partly by tidal heating from its resonance with other Saturnian moons. We've identified potential tidal heating in Triton, Neptune's largest moon. The principle is clearly not unique to Io, but Io is the most extreme expression of it that we've confirmed, and its extreme nature is precisely what makes it informative. It's the upper bound on what this mechanism can produce. Everything we learn from Io tells us what to expect and what to look for when we eventually examine similar bodies elsewhere. Here is something that doesn't appear in most discussions of Io, but is worth considering carefully. The volcanic gases that Io continuously exhausts into space, primarily sulfur and sulfur dioxide, do not simply float away. Jupiter's magnetic field captures them. They become ionized by radiation and trapped, forming what's called the Io plasma torus, a donut-shaped ring of charged sulfur and oxygen ions that follows Io's orbital path around Jupiter. This torus is not a trace phenomenon. It's one of the brightest ultraviolet features in the solar system. It interacts with Jupiter's magnetic field in ways that affect the planet's own aurora, driving electrical currents along magnetic field lines between Jupiter and Io. The two bodies are electrically connected. There is a flux tube, a channel of electrical current that flows between them, carrying roughly 1 trillion watts of power. 1 trillion watts. For comparison, humanity's total global electricity generation is roughly 25 trillion watts at peak. The electrical connection between Io and Jupiter is therefore equivalent to about 4% of all human electrical generation running continuously, driven by nothing more than orbital mechanics and the physics of charged particles in a magnetic field. This isn't a metaphor for something larger, this is a direct statement of scale, and it implies that Io is not merely a passive body being squeezed by Jupiter. It is an active participant in a circuit. The two objects are coupled gravitationally, tidally, electrically. Io shapes Jupiter's aurora, influences the structure of its magnetic environment, and seeds its radiation belts with fresh material. In a system that science tends to describe as a planet and its moons, the relationship between Io and Jupiter is closer to mutual than it is to subordinate. That changes the way you should think about what a moon is. We tend to think of moons as passengers, smaller bodies carried along by the gravity of something more important. Io is not a passenger. It is an engine in a coupled system, and the system would behave measurably differently without it. The Galilean resonance that keeps Io tidally active also prevents Europa from freezing solid all the way down, because Europa is also heated more mildly by the same resonance. Without Io's extreme volcanism continuously cycling material into the plasma torus and reinforcing the orbital resonance, the subtle tidal heating of Europa might not be sufficient to maintain its subsurface ocean. The ocean on Europa, the one we're sending the Clipper to search for life in May, in a meaningful physical sense, owe its liquid state partly to the dynamics of a world on fire 400,000 kilometers inward. Think about that chain carefully. A volcanic moon that's too radiation-soaked and too dry to support any life we recognize, helping to maintain the conditions for the existence of an ocean that might support life we haven't recognized yet. This is what interconnected system dynamics looks like at a solar system scale, and it's the kind of relationship that's almost invisible until you look at the whole system simultaneously. We don't know how stable the current Laplace resonance is over the very long term. The same gravitational interactions that maintain the resonance are also very slowly transferring angular momentum between the moons. Over timescales of hundreds of millions to billions of years, the resonance configuration will shift. The tidal heating will change. Europa's ocean may freeze. Io's volcanic activity may diminish or concentrate or cease. The system we're studying now, this specific snapshot of a 4 billion-year-old ongoing process, exists in a particular configuration that won't last forever. We are observing it at a moment in its history. That moment may not be representative of its past or its future. This is one of the recurring discomforts of planetary science at scale. The universe operates on timescales that dwarf human experience, and the configurations we observe are essentially instantaneous snapshots. Io's current volcanism, Europa's current ocean, Jupiter's current magnetic structure. These are all one frame in a very long film, and the frames before and after look different. When we draw conclusions about what a system is, we are really concluding what it is right now, at this moment in cosmic time as seen from one specific vantage point in space. That's a humbling qualifier to attach to every model we build. There is an observation made during Juno's flybys that hasn't been fully resolved. Some of Io's volcanic eruptions appear to be producing heat outputs that exceed what the tidal heating model predicts for their location. Not by small margins, by factors large enough that the current localized magma pocket model, which is itself already a revision of the global magma ocean model, may need further revision. Either the magma is distributed differently than the gravity mapping suggests, or there are additional heat sources operating in those regions, or the thermal conductivity of Io's crust varies in ways that concentrate energy in unexpected places. This is not a settled question. It's an open one, and the data to resolve it doesn't currently exist. Science communicates its confident results. It's less good at communicating how many open edges there are in even its best understood subjects. Io is a case where the open edges are large, and they point in directions that could substantially change our understanding of how tidal heating works, which would then change our predictions for tidally heated bodies elsewhere, which would change what we expect to find when we look. The uncertainty at Io ripples outward. Let's come back to that strange sulfur chemistry thought from earlier. One of the more speculative but scientifically literate lines of thinking about Io involves what its extreme chemistry might look like from the outside. If there were another civilization in the galaxy looking at our solar system, not with our instruments, but with instruments somewhat better than ours, capable of analyzing atmospheric compositions spectroscopically from a distance, what would they see at Io? They would see a body surrounded by sulfur compounds in multiple oxidation states, embedded in a powerful radiation field, connected by electrical currents to a massive magnetized planet with surface temperatures ranging from -130 degrees Celsius to over 1,600 degrees Celsius in active lava zones. They would see an atmosphere that oscillates in pressure with the day-night cycle. They would see volcanic plumes reaching hundreds of kilometers into space. By every standard criterion we use to assess whether a world could support life, they would conclude, no, Io cannot support life. And they would be right by the criteria we've established, which are based entirely on the chemistry of Earth life and which have never been tested against any other biology. The criteria might be correct, or they might be the specific solutions found by life that originated in a warm, wet, radiation-protected environment, not the only possible solutions in a universe full of environments that don't fit that description. This doesn't mean Io has life. Almost certainly it does not. But the deeper question whether life requires the specific conditions Earth life requires, or whether those conditions are just the only ones we've been able to study, is not answered. It is not close to answered. And every time we find a place as chemically active and energetically wild as Io, and rule it out based on criteria derived entirely from one data point, we should do so carefully. The absence of a dedicated Io mission in the context of all this feels less like a gap in exploration and more like a structural blind spot. We are sending a spacecraft to search for life in Europa's ocean, an objective that makes scientific sense, but the system that may be partially maintaining Europa's ocean is going unstudied. We are modeling tidal heating on exomoons to predict where life might exist elsewhere in the galaxy, but our best local specimen of tidal heating is currently unmonitored. We are building frameworks for interpreting exoplanet atmospheres as life detection tools, but we haven't fully characterized what an intensely volcanically active, tidally heated world's atmosphere looks like at high spectral resolution. All three of those gaps trace back to the same place. Io is waiting. The volcanoes are still erupting. The mountains are still pushing upward from the compression of a resurfacing crust. The plasma torus is still glowing in ultraviolet, carrying charged sulfur away from the moon and feeding it into Jupiter's magnetic envelope. The ground is still moving 100 meters up, 100 meters down, every 42 hours as Jupiter squeezes and releases and squeezes again. None of this is metaphorical. This is the actual physical behavior of an actual world, operating on an actual timescale right now. What we know about Io was hard-won over decades of flyby missions and Earth-based telescope observations, assembled piece by piece into a picture that is still incomplete. The picture we have now is more complete than the one Galileo had when he pointed his glass at Jupiter in 1610 and noticed 4 small points of light that moved night by night. It is also, almost certainly, far less complete than the picture we'll have a century from now if we choose to look. The question is always whether we choose to look. Something worth noting in closing. The Laplace resonance that keeps Io volcanic also, as we discussed, may be what maintains Europa's ocean. But there's a third body in that resonance, Ganymede, and it too receives tidal heating at a lower level. Recent observations suggest Ganymede may have its own subsurface ocean of liquid water, larger by volume than Earth's oceans. The JUICE mission, arriving in 2031, will orbit Ganymede and attempt to characterize this ocean. If confirmed, the solar system will contain at least 2 subsurface oceans, Europa and Ganymede, both of which owe part of their thermal state to the same orbital resonance that makes Io volcanically extreme. 3 moons. 1. Resonance. An ocean potentially habitable by our criteria, an ocean potentially habitable by unknown criteria, and a volcanic world so strange we haven't fully modeled it yet. All of them connected, all of them shaped by the gravity of a planet they can't escape, and all of them, in a sense, downstream of a chain of physical processes that started with the way the solar system formed and the specific orbital ratios that happened to emerge from the chaos of early planetary migration. The chaos wasn't random, of course. It couldn't have been. The universe runs on physics, and physics is deterministic at this scale. The orbital resonances, the tidal forces, the volcanism, the oceans, all of it follows from initial conditions set at the beginning of the solar system. And if initial conditions elsewhere in the galaxy produce similar configurations, similar dynamics follow. Similar volcanic moons, similar ice-covered oceans, similar complex chemistry and radiation environments we'd normally dismiss. How many of them are there? We don't know. We've barely looked. But here is what Io tells us. The assumption that worlds at cold, distant orbital radii are frozen and simple and uninteresting is wrong. It was always wrong. We just lacked the instrument sensitivity and the close approach data to see the complexity hiding in the dark. Now we have some of that data, and the picture it's showing us is far stranger and far more interconnected than the model it replaced. There is a version of this where we stop here, with Io understood as a remarkably dynamic volcanic world in a gravitationally coupled system, and call the story complete. But the version where we stop here has a problem. It doesn't account for what tidal heating means at the galactic scale for worlds orbiting stars far more active than the Sun, for moons around gas giants in systems with entirely different planetary architectures, for the possibility that the frozen outer reaches of other solar systems are studded with worlds like Io, burning invisibly in the dark. That accounting is still missing, and it matters more than the volcano count on a moon 600 million kilometers away, because it changes the arithmetic of how often complexity emerges in the universe, and complexity, wherever we've looked for it, turns out to be the prerequisite for everything that interests us most. Io is a data point, but it's a data point pointing at something much larger, and we've only just started to read it.